The AI industry is saturated with fragile wrappers and toy demos. They execute flawlessly in a controlled sandbox, but the moment you put them into a messy, multi-step enterprise workflow, the illusion breaks. The most common trap engineering teams fall into is treating AI like an autonomous worker. They allow a probabilistic model to write extracted data straight to a production database or system of record. That direct write approach causes an immediate authority inversion. The AI becomes the author of record for business data, operating with total autonomy over fields that dictate real-world actions, like billing, scheduling, and client outreach. As a result, highly paid human operators are forced to act as data janitors. Instead of doing their actual jobs, they spend their days forensically cleaning up silent AI hallucinations that look superficially correct but contain factual errors. Standard DevOps practices and automated worker paradigms break down here. DevOps is a methodology that combines software development and IT operations to ensure predictable software delivery. But you cannot treat a system that guesses the same way you treat a system that strictly executes deterministic logic. To survive production, engineers must treat the AI as an untrusted drafter. The system must wrap the model in deterministic infrastructure that forces accountability before any data touches the database. Resilient enterprise AI requires code-level structural constraints. Engineers must build UI-bound contracts and welded kill switches to protect user trust from probabilistic drift. We solve the authority inversion by changing where the AI is allowed to write. The model populates an interactive UI form instead of a database table, establishing that form as a strict operational contract between the machine and the human. UI is the user interface, the graphical layout where humans interact with the software. This architecture requires streaming extraction to succeed. Users need time to first value, meaning they can start reading and editing fields dynamically as the data arrives, rather than waiting for a monolithic backend process to finish its entire run. This diagram illustrates a wireframe UI form progressively populating with extracted data. To make this volume of data reviewable, the interface introduces per-field confidence badges, guiding a human operator's finite attention exactly to the individual data entry boxes that require scrutiny. Fields scoring above 0.8 get a high-confidence green badge. This signals that the extraction is mathematically clean, and the human can safely trust the value and move on to the next task. But when the model infers a guess, it drops to the medium or low confidence tiers. These badges act as a visual warning, demanding human verification for complex or ambiguous data, where the model is likely to hallucinate. This visual triage prevents review fatigue. You are only asking the user to audit the AI's weak points, rather than forcing them to proofread every single line of text. There is an iron law to this design. The AI's confidence scores are strictly advisory, no matter how high the threshold reaches. Enforcing the human's overwrite as the ultimate authority restores workflow accountability. User edits are final, preventing polluted AI-generated records from entering the downstream system. Once the human approves the form and hits submit, the back-end process takes over. The naive approach here is to simply take that final human-edited record and write it to the database, discarding the intermediate steps. But overwriting the AI's original draft destroys the exact feedback signal needed to improve the model. You lose the ability to tell whether the AI was objectively wrong or if the source email itself was just ambiguous. This diagram shows a JSON payload package splitting into two distinct routing branches. JSON, or JavaScript Object Notation, is a standard text-based format used to represent structured data. The system must preserve what the AI originally produced alongside what the human actually submitted. The backend explicitly isolates the diff. It calculates the exact mathematical delta between the AI's initial guess and the human's final edit. This diff is stored as first-class data in the learning signal pipeline. This creates a perfectly clean, highly specific dataset mapped directly to human decision-making for future model fine-tuning. Capturing this delta explicitly changes the nature of the workflow. It transforms a frustrating manual correction from a human operator into an automated, deterministic learning loop for the system. Data integrity is only half the battle. Once you introduce AI orchestration and multi-step agentic behaviors, you face a completely different class of deployment risks. These are behavioral failures. A classic example is an LLM equipped with a tool to ask clarifying questions, which gets stuck in an autonomous clarification loop and refuses to execute a task. An LLM, or large language model, is the core AI engine that processes and generates human-like text. This timeline illustrates a fast-paced user workflow being permanently halted by a repeating AI question loop. Asking constant clarifying questions technically improves the model's data precision, but it destroys the user's workflow momentum, devolving a single-step action into a multi-step negotiation. Standard DevOps practices fail to contain these risks. Relying on an off-by-default environment variable feature flag is structurally inadequate for managing AI behavioral failures. In a distributed system with multiple deployment pipelines, an ops team or a stray deployment template can accidentally re-enable that environment variable. The background deployment toggle ends up casually flipping to true, causing spontaneous, undocumented UX regressions. UX stands for user experience, encompassing all aspects of the end user's interaction with the company, its services, and its products. A technical code crash is loud and generates stack traces you can debug immediately. An AI behavioral regression operates silently, looks superficially helpful, and actively erodes user trust. Because these behavioral failures actively damage core user trust, they require a containment strategy that is structurally irreversible, not just a quick operations toggle. The strict architectural solution to this behavioral drift is what we call the welded kill switch. This diagram shows a logic gate visualizing a hard-coded code-level constant paired with an environment variable. When you pair a code constant set to false with an environment flag set to true, the system evaluates the condition, resolving definitively to false. This design creates intentional operational friction. To re-enable a risky AI behavior, an engineer must edit the actual codebase, pass a pull request review, and push a new deploy. But you cannot just kill the AI feature and leave the user with an error screen. The system has an operational requirement to still fulfill the user's request, even when the AI path is welded shut. Traffic hitting the kill switch is deterministically forced down a dual routing pipeline. It falls back to a maintained, predictable legacy path that requires no AI orchestration to succeed. This sets a clear triage rule for engineering teams evaluating AI failures. Highly recoverable failures, like an imperfect search ranking, get standard runtime flags. But trust-damaging failures, like AI behaviors that block human workflows and demand constant clarification, absolutely mandate the welded code-level switch. The welded kill switch prioritizes long-term system integrity and user momentum over the convenience of a quick operations toggle. This macro blueprint shows the complete, resilient enterprise AI architecture. Zooming out reveals the UI streaming loop with diff storage on the left and the API router with the welded kill switch on the right. Building this requires a strict shift in engineering mindset, discarding the fragile assumptions of AI sandbox demos. Structural production issues like amnesia, hallucination, and workflow blocking cannot be fixed by merely tweaking a prompt. They require hard, deterministic infrastructure. The ultimate reality of modern software development is this: probabilistic models raise the baseline capability of a system, but deterministic architecture dictates its reliability ceiling. By forcing the AI to draft via a human-approved UI contract and enforcing code-level guardrails, engineers safely deploy AI into high-stakes workflows without sacrificing accountability.